So this is part three, and so part one and also part two. If you haven't checked those out, part one is laying the foundations, creating the game. Part two is then Minimax bot, the Minimax algorithm. But this part three is what the very reason I actually created the game. It's reinforcement learning, more specifically Q learning, and we'll be checking out what it is, how it works, and how is it that we can reward good behavior and punish bad behavior and ultimately get a bot that can mimic a very decent strategy or an unbeatable strategy. Let's check it out. Q learning. The first thing that we see is when we open up Wikipedia is it's a type of reinforcement learning algorithm. Now, reinforcement learning is something that the very reason I actually created this game, TicTacToe, is I wanted to try reinforcement learning. And it's very similar to the way that we as humans reason, or that we can train animals or our kids, ourselves. Like it's much easier to reason with and understand on a conceptual level than something like neural networks, with the various neurons and hidden layers and all that. It's quite an abstract concept. Even things like regression, you really have to visualize it and show it on a 2D plane to kind of make sense of what an algorithm is doing. But reinforcement learning, I find, is a little bit closer to something that makes sense to us. So, as the name implies, reinforcement and learning. So we learn something and then we reinforce positive behavior, and we discourage negative behavior. So if I were to take the example of we get a new puppy, and the puppy pees in the house. It finds a nice little carpet in the house and it feels great, and puppy decides this is a good spot and it pees. Now the owner grabs the puppy and he says, hang on. He, a little bit frustrated with the puppy, maybe puts it outside and says, no, pee in the grass, puts it on the grass. So the puppy senses, no, I've done something wrong here. This owner doesn't seem too happy with me. Right now, the next day, while the puppy's running around on the grass, it pees on the grass, and the owner is giving it lots of love. Oh, well done, puppy. You've done excellent. And suddenly the puppy realizes, hang on, I pee on the grass and I get praised. I pee on the carpet and the owner seems dissatisfied. So clearly I need to pee on the grass more. And so what happens is the puppy, through reinforcement learning, learns that this is good. And essentially after a while, it just knows peeing on the grass is good, peeing on the carpet is bad. Making this a little bit more concrete, let's have a look at the concept of reinforcement learning. It involves an agent, a set of states, and a set of actions per state. All right, let's just look at those three concepts. And they're very high-level generic concepts, and I'll explain why that's important in a moment. But if we take a look at this, we've got the bot that we're training. He's the agent. So this bot's the agent, and then we've got the state. This is what the board looks like. It's the current state of the board or the game. And state would also include, is it my turn or is it the opponent's turn? So that's not depicted here, but in this case, it might be X's turn. And the new state, so it's a set of actions it can take. It can put it there, and X in one of those. Once it's put a set of an action down, it transfers to a new state. But let's just look again. So we've got the agent, the bot, the state, which is the board, and a set of actions, and those are the empty spots. Now, I jumped the gun a little bit just now, mentioning over here, by performing an action, the agent transitions from state to state. All right? So by performing an action, let's say we chose that spot, that action on this state, and then we transfer to a new state. And now we're on the state. And then the last part, executing an action in a specific state provides the agent with a reward, a numeric score. So in this case, we look at the state, we see we won, so we want to say it's a positive reward. And then therefore, we, same as with the dog, we encourage it. You peed on the grass, great. We give it lots of love, maybe give it a treat. We give it a positive reward saying this was good. Finding yourself in this state, good, well done, is the correct move to make. So what is Q learning? And so Q learning deals with Q, or the Q value that we want to calculate, is a function that the algorithm computes, which is the expected rewards for an action taken in a given state. So if we take a look again here, we want to take an action and we get into this new state, and the Q learning, or the Q value, basically has a Q table where we look up to say, what is the score if I were to put the X here? That's a positive score. What is the score if I were to put it here? And here what I've done is I've drawn a little table. Now this is the state just drawn out, and if you remember from the previous videos, we've just using an integer, a flat integer instead of a tuple to depict our state. And but one thing I've added is you'll see there's 10 characters, not 9 as in the board. The first one indicates whose turn it is. And this is very important, because if it's O's turn, this is a wonderful state to be in, because it's your turn, so you'll win the game. If it's X's turn, it's a wonderful state for X to be in. So whoever's turn this is, it's important, because if it is X's turn, this is a terrible state for O to be in, and we should discourage finding yourself in this state if you're O. So the first one is we're saying we are X, player 1, and then the states. So 1, 0, 1, which depicts this 1, 0, 1, 0, 0, 0, 2, 2, 0. That's all how what we do. So the Q table is something we'll create and train, and we look up the state and we say, all right, here I've got a state and the possible actions. My actions are, this is a 0-based index, so 0, 1, 2, 3, 4, 5, 6, 7, 8. So 1, 3, 4, 5, and 8 are open. So I can choose one of those steps. If I choose 1, I'm going to win. So the trained policy will indicate quite a positive score. If I choose 3, 4, or 5, I'm going to end up losing the game, because the next turn it's O's turn and he's going to put it over there, and therefore I lose. And so 3, 4, and 5 are very bad. 8 is an interesting one, because I will block O from winning, and either likely end up in a draw, or maybe in this case, if I play well, I should actually find myself in having 2 spots to win with. So you should win, but it's more likely to be a draw if you're going to be choosing something like that. So it's a lower score, for instance. So the best score would be definitely 1, because I'm going to win the game immediately. So Q learning involves a Q table where we calculate from this given state what are the possible actions and what is the score, the numeric value for choosing a certain action. Now earlier I mentioned that that it's quite a generic concept, this reinforcement learning. And if I scroll down over here to just show the Q table we've got in Wikipedia, let me see if I can zoom in a little bit. Whoopsie. So here we've got an initialized Q table. So we have a bunch of states, and I can make an action either move north, move south, east, west, pick up, drop off. So a bunch of actions I can take. And once I've trained it, they've got a certain score. So it'll be better for me to do something in this given state, and I'll end up training that. Now, the concept here has nothing to do with TicTacToe. Now, once again, if you look at this, um, we as humans will look at this and say, oh, of course, this is the best spot because it's 3 in a row. Now, Q learning or reinforcement learning has no concept of how this game even works. Although once we've got a trained policy, it certainly looks like it's intelligent, but it actually isn't so much. And why I say that is it doesn't have context like, oh, okay, tic-tac-toe means I have to block the other person or ultimately get 3 in a row. And when I get 3 in a row, it's a good thing. We're just saying, here's this arbitrary state. It sees the next few actions, which means I'm going to find myself in this state, over here, or that state, or that state, or that state, or that state. What's the best move to take? And we've just trained it to say, all right, go there, go there. And this is very similar to the dog. The dog might still not know, I don't know why I mustn't pee on the carpet and why the grass is fine. To me, they feel the same under the feet and everything. But for some reason, my owner discourages me from peeing on the carpet. And it's very similar here. And why that's important, there's two things there, is if this game is mirrored, for instance, the zeros are on top, the x's are at the bottom, the state will look different, and the game will have no concept of, okay, 3 in a row, I'm actually just missing one and I'll win the game. If the state hasn't been trained, it won't know what to do. Human play will pick it up immediately. Oh no, it's the same state, it's just mirrored, or it's just the other way around. Or even if I just put this 0 there, and keep the x's on top there, it's a new state, which means it's a new Q table value, which means if we haven't seen this state before and we haven't trained it to say this is a good state before, it won't know what to do. And that's very important to note, because we end up having to define all the given states, or at least most of them, to accurately play a solid game. And there are ways of doing function approximation and other ways around where we could, for instance, say, instead of having a state like this, our state could be where we worked it out to say, is 2 in a row with space, something like that, is true. And, or if not, is this, and we have certain states which depict some form of meanings like rows and columns and diagonals. So we would have to featureize those things. And then within a given state, it might then pick up mirrors, for instance, and say, okay, well, 2 in a row with 1 in the middle is the same there or there or there, etc. But because we've gone for purely a state, it means just the 0 moving there instead of there, or there instead of there, will completely be a new state. And if it's not trained, you might see some surprising results. So every time it's going to pick here, but if as 0, instead of you putting it there, you put it there, you might completely throw it off. And that's something you'll see when we test out the game. So you might find a state that hasn't been trained yet, which means that it will then be unsure what the best move is and end up choosing maybe the less optimal move. The great thing, however, of it being such a generic concept of it's just a state with a set of actions is you can apply the exact same logic algorithm, and most of the code you can transfer to almost any other game. If we were to play that Chrome game where the internet is down and you have to jump, for instance, you could have a state saying, how far am I away from the tree? And it would learn that, okay, when I get to, a certain distance, my state would be maybe my speed and distance from a tree and height of tree or bird or something. And essentially the action would be do nothing, just keep running, press up, which is jump, or duck down. And through different random iterations and training, you could eventually train it in a certain way where the reinforcement learning will know, okay, when at a certain speed, at a certain distance, at a certain obstacle, up always works. And therefore, when it encounters that state, it will jump. And so the exact same concept, almost the same code will work. The only difference is the way you depict your state is important, and the way that you give rewards will depend on whatever game or application. But that's the beauty of this. So you can apply it to many different applications, especially with games. Jumping back to Wikipedia then, excuse me. So we looked at the Q table, and now the actual algorithm to calculate the Q value. So if I'm looking at a value in the Q table, I actually have to calculate it, give it something. What you'll see is something that looks rather intimidating, but it's not actually if we break it down. And I won't dive too deep, but basically we're saying the Q value, the new value that we're calculating, let's assume it's let's go back maybe over to our board over here. So the new value that we're calculating, let's say 1, would be the old value, which was 87, plus learning rate times reward plus discount factor times the estimate of optimal future value minus old value. So this would be the 87 again. So 87, learning rate and discount factor are set things. I'll touch on them now. And then a reward. So TicTacToe is slightly contrived from this in the sense that we don't actually get a reward for making a move that's not a terminal state or an end game. Because, like, let's say you make the first move and you put it in the middle. Is that a good move? Is that a bad move? How do we give it a reward? I mean, are you going to win the game or not? It's difficult. It's actually impossible to say from so early on. It depends on your next moves. And so what we end up doing there is we don't have a temporary reward. So there's that temporary reward, but we will have an estimate of optimal future value, your future reward. And so what we're essentially doing is we finish the game, we're capturing all the states up to that point in the game. And once we get to the end, we say, great, we won the game. This was a good game. Now, jumping back here and looking at this. So this is a good state if you're X. Now, if this is a good state because you won the game, that means this was also a good state if this is your turn, because we're one step away from winning. So we want to find ourselves in this state. Great. And if this is a good state, then we want to find ourselves in a state one before this one. And so we're basically feeding a reward backwards, or back propagating a reward, saying ultimate state was very positive. Then the reward before that was also positive, the state, sorry, and etc. And we go all the way back. And the discount factor there would in this case help with regards to, so for instance, we might say the ultimate reward, you get 100 because you won. Then this state over here is 80 because you're just about to win. And the state before that is maybe, etc. 80% of the previous one. And so we give less value to the first move because the first move has many options. If you start in the middle, you could lose the game, you could win the game, you could draw the game. We shouldn't give it too high a value, but we want to give it some positive value still, because ultimately starting there has led us to win. But as we get further, the values of the positive values get greater. Now I've mentioned the learning rate and discount factor. And just very briefly, learning rate is something that tells us if I've already got a Q value for this state. So let's say the middle block when we start is fairly positive. If I have a very high learning rate, which considers only the most recent info, so now I were to lose the last game, so 9 games I won starting in the middle, the last game I lost, I would suddenly overwrite it to a negative value, because the last game is the last game we've trained, which I've lost. So a high learning rate would be very much recency bias. Very low learning rate would say that, well, whatever's in the Q value, if the Q value says if being in the middle is negative, then no matter how many times I win by starting in the middle, I'm not going to really update anything. So we want to play around with learning rate a little bit and kind of say it needs to be low enough so that one odd game towards the end won't throw out all our accurate calculations. You know, the edge case isn't going to overwrite the legit cases. But if we initially got the Q value wrong, then having a low learning rate is going to take a long time. Let's say we said something is negative, but it's actually positive. We just happen to, on our first game, lose. You know, 1 game in 100, you might lose. So it's going to take a lot of games for us to then override that learning value to become more realistic. Discount factor, that's something that plays a bit more with when you get temporary rewards and your future rewards. So, but I've used it for the discount factor of, you know, the last state you maybe get 100 if you win, and then discount factor is the state before that you should get a little bit less, but still should be positive because it led to that winning state. And then from there you discount some more, a little bit less. And that's what I've used it for. But if you have a temporary reward, it plays it a little bit differently. And that's what you'll read over here is where if you think of the game Snake, for instance, you know, that good old Snake game where you have to survive and then eat the apple. If we said, okay, the future reward for eating the apple is 100, but our discount factor is 0, what you'll see is it says it's myopic or short-sighted. So 0 times 100 would be 0. So basically the apple's rewards counts for nothing. And we actually discouraging it from the future reward, and only the temporary reward comes into play. So it's short-sighted. It's only the next state's reward. The next state's reward could be, we give it a little reward of 1 for not dying, for instance, not crashing into a wall or itself. By doing this, we'd end up having the snake, go up, left, down, right, up, left, down, right, and be happy with that because it doesn't consider, I should rather go for the apple, it's worth more than just surviving. The other extreme would be that the temporary reward doesn't count for anything, but the ultimate reward counts for something. So that's something you can play around with. But in TicTacToe, we've just used it as the final state. You get a full marks. The one before that, you discount some of it, but you give it a value in some of it. So we discount lower and lower until the first block still gets a positive value because it ultimately led to a win in the end. But let's get into some code. So we've got a Q learning bot which implements iPlayer, and from previous videos you'd seen the iPlayer. We need to override the make move, and we get the game state in, and we need to do something smart and return an integer. So that's the important method over here. And then there's one other one that for the first time we'll use, because we didn't use it for Minimax or the random bot, is the game ended state. Now that the game's ended, we need to back propagate or feed the reward for all the states prior to this to calculate the rewards. So just looking at the make move, we've got firstly this part up here, and I'll get to that now. That's the exploration rate. We basically choose an exploration rate of maybe 80%. So 80% of 20%. Where you would say for 20% of the time, don't use the policy or the best move that I know. Rather pick with choosing something random, and then basically the exploitation is the one that we were talking about the whole time. I'll get to exploration now, why that's important. But exploration, we look at all the positions we have. We look up the policy, essentially the Q table we've stored, and we basically say, what's the next move? What I've done is we look at the next position, so all the available positions draw out that state, and we're basically saying, okay, if I were to move in this spot, this is what my next state would look like. Look it up on the policy and say, is this a good thing? Is this a bad thing? And we look up and say, that's a great thing. Therefore, make that move. We pick the best move and return it. That's our exploitation. Now, exploration is quite important because let's assume we gave a slightly positive reward for a draw, which we did. But and the very first game, two Q learning bots against each other, they work out, it turns into a draw. It's a positive reward. Now, if we don't know what move to make, we choose 0. But because the first game was positive, the next game, if we just only do exploitation, it will look up all possible moves and it will pick the last game it played, which is a positive score, and it'll always choose that one. And no matter what we do, it will always choose the same move over and over and over again without ever realizing, hey, there might actually be better moves. So if we were to illustrate that in a picture of a mouse in a maze, it might be a very simple maze where the mouse just has to walk straight and then left and then he's out, for instance. But the mouse ends up turning into all the dead ends back and forth, in and out, some of them several times, and eventually it escapes. And we say, all right, that's a positive result. Now, the mouse will always follow its positive results because some of the other policies, it doesn't know the score, so it'll be 0. So it'll always follow that path, not realizing there's an easier path. So we have to set an exploration if we're going to train effectively. And the exploration rate essentially then allows us to say, all right, you usually turn right in this maze, but just this time choose left, just for interest's sake, just see how it happens. And if we're doing tens or hundreds or even millions of iterations of training, we're hoping that through exploration we'll explore the entire game state while still converging to an exploitative strategy and sort of solidifying the fact that what we're saying is a good move is essentially a good move, whereas you might find that there's a better move, or that it was only a good move because the opponent didn't choose the best move where they would have won, etc. So the exploration should find those things and then converge to something better. Now looking at game ended, and we're basically looking at feeding the reward. I've given a win 100 and a loss minus 100. And in retrospect, this wasn't a good call here, the draws. If you started first and you drew, I said it's 20, which is a fairly high score. For starting first, you kind of want to maybe stick to 0. I don't think negative is a good idea because essentially if the bot gets so good, it's a solved game, TicTacToe, and you'll only be ending up with draws, and eventually the best moves you can make will end you up in a draw if you play the best opponent. So you don't want to start to over time discourage that. So you want to keep it either level at 0. I think that's too high. I do think having a slightly higher reward for a draw if you play second is maybe a good choice, but these are too high. But basically what we do is from both perspectives, we feed the reward twice. Basically from my opponent's perspective, the X, let's say for instance, is my reward, and then the opponent is O. And we want to basically see, we don't want to just train from my perspective, because I or the agent, the bot, might find itself being O in the same position as its opponent, and you want to learn from your opponent as well, whether it's a human player or if it's, so you want to learn both perspectives if you find yourself in them. So discourage the loss, encourage the win, for instance, etc. So that's that. And then the policy itself that we're looking up. Sorry, let's quickly look at the feed reward. We're just looping from the states, all the states in the game that led up to the terminal state or the end game. And this is, you can see, kind of taken from Wikipedia The old value, learning rate, those are set. Reward, and then the old value again gives us our new score, and then the new score we update the Q value for. Now policy may seem it's this sophisticated model or something, but it's as simple as you get. If we look at the type, it's a string, it's a dictionary with a string and a double. And to see it visually, this is the saved policy. We're basically saying this is the state, this is the value. That's all it is. And so when we save the policy, we basically just serialize. It's easy as that. Take the policy, serialize it to JSON. It just makes it easier for me to read, and then save it. And when we load it, we deserialize it again back to a dictionary, and that's it. And so once again, when you're looking it up, we end up looking at the next possible move, looking it up from this dictionary and say, yes, I know, or if I don't know, it's a 0, which essentially replicates the Q table over here. If we don't have the value, it'll be 0, and if we do, we'll look up the value. So let's get to the fun stuff and actually play against this Q learning bot. So if you go to TicTacToe.filteredcode.com, you'll see that I've now hosted it, and you can also see if you use the code and you clone it and run it, you can run it locally as well. But there's a new option here for Q learning bot, and there's a few different policies. The one is untrained, so it's an empty policy. Think of the Q table with all initialized to 0 every state. Then there's one with some training, so there's some form of strategy, but not that comprehensive. And then finally the one is that's highly trained through Minimax, through human training, and through training against itself for many iterations is highly trained. And a bit of a fun experiment here. Hopefully it doesn't turn out as bad as Microsoft's Twitter AI bot that they created. What was that thing's name? Tai, which really went downhill very quickly. But the idea of this community trained is that you play against it, and it will then upload the results, and if somebody else plays against it, upload the results and train the policy. Essentially, the more we play, we as the community, whoever plays against it, the better it will become, and eventually it will become as strong, if not stronger, than the highly trained one. Or it can become worse if if we end up asserting that a poor start actually ends up you winning. So you can also train it poorly as well. But looking at for instance, all of these are training ones. So if you look at the untrained one, you'll see it starts over there. Maybe what we'll do is we'll do this. Now we're going to encourage it to say, let's say over here, if I start here, this is a positive move. So I go there. Okay, well, let's do that. And let's do that. So hopefully when it starts, there we go. It's learned from me that, hang on, if I started there, it ended in a positive result. So it's learning as we play it. But once again, if you exit the game and later you come back in, it'll just be a fresh one again. Whereas the community trained one will be keep its state. So for instance, there we go. It did the exact same moves as I did because I copied the same moves. And had I, once again, remember, it looks at identical states. So had I, even though it started there, had I then pushed and gone in the middle, it would have seen it as a completely unknown state, and it wouldn't have followed the same pattern. Because it doesn't understand that, hey, I'm going down in a row. It just knew, hey, this exact same state ended up for a win for me just now. Therefore, it thinks that's a good state to be in. Cool. So feel free, play against the Q learning bot. And the highly trained bot, just for interest's sake, is almost unbeatable. And the reason I say almost, and I'm going to throw this challenge out to Benny, because he just seems to beat anything I throw at him. So even the escape room. So he just goes straight and cracks the final code without any of the clues. Um, so Benny, this one is for you. But basically, the highly trained uh, bot, if we look at the policy, this is the policy for that one. We have, if we exclude if we look at the lines, we exclude the top because it's got a brace in the bottom. It's got 946 entries. But remember, every state we duplicated because it's got the perspective of from a 1 and from a 0. So it's 9946 divided by 2. So this thing has seen 4,973 unique states. Now here's something interesting. Just keep that there. And we go to a game complexity. Now in Minimax, we did a quick Google and we found there are 255,000 possible games. And I thought, no, that's surely too many. But with a bit of reading over here, I found that was true. But games would be, for instance, if I start with X on top and then the next move X in the middle, it sees it a different game as if I start X in the middle and then X on top. Whereas from a state, they're both X's top and middle, for instance. But because you started in a different order, it sees a different game. So looking at the number of legal states that you can find yourself in, because that's what we care about. So we don't so much care about how did he get into the state? Was it this one first, or was it this one first? We're just saying, okay, whichever one is first, this is the actual state, unique state on the board. You get 5,478. So if I were to do that, I know I should do it the other way around, but this will work as well. So if I say 5,478, that means there are 500 states that this bot has not seen before, which means when it gets into that state, or it needs to choose to make one of those 500 states, it wouldn't know which to make, and it'll choose the most positive move that it knows. And there might be a more positive state, so it is still beatable. And I have left open a little bit of a door for training it, so you can, while you're playing it, it does train from your session that you play with it, and so you could try to lead it in a certain way by reinforcing a certain pattern and then trying to exploit it in a different way. So yeah, that's something worth noting. So challenges out there, if you can beat the highly trained, I will be quite impressed, but in theory it is doable. And then just geeking out a little bit more with regards to how highly trained is highly trained. So I've got a spreadsheet here that I just captured some of the results. So I ran this bot against a random bot, did 1 million games, and so about almost 950,000 it wins. So it wins about 95%. And about 5% is a draw against a Q-learn bot itself, essentially, but with 50% exploit, which means half the moves it's going to try random, half the move it's going to try. The idea was random might just be too random. If we found a state where there was actually a move to win it and we didn't take it, then I wanted to just see, maybe with a bit of strategy, but 50% of the times it just chooses something random. And then I tried again 90% of the time. But you'll see all of them losses are 0. And then finally Minimax. Now I could only run about 10,000. Well, I could run a lot more. It just takes a long time. Running all 4 of these is far faster, these 4 million, than it is to run 10,000 Minimax. And that's once again because Minimax explores every single possible state on the board to make the best choice. So we're looking at it looks at 5,478 possible moves before it makes one move. And then you choose the next step, which will then go down in a tree based on all the available moves, etc. And so a game takes a little bit longer. It's a bit slower. But so one thing that's also very interesting is that, and this is because my learning rate was quite low. So my learning rate was 0.2, which is actually a bit higher than Wikipedia's suggestion of 0.1, but it is fairly low, which means that if, for instance, you start training your Q table with incorrect values or values that aren't the best, it takes more iterations to correct. And what I found is if I play an untrained bot against another untrained bot, the Q learning, and they eventually, after 1 million games, I went against each other, 1 million games of training. I then played against a random bot, and I was quite surprised that after 1 million games of training, it still lost almost 10% of its games to the random bot. Yes, it did win, almost 90%, but still, random bot with no strategy could beat it almost 10% of the times after 1 million iterations. And some of the other articles I've looked at various people doing the TicTacToe, most of them, or pretty much all of them I've seen, are Python, and some of these guys claim 200 to 300,000 iterations, and it's unbeatable. So clearly my parameters aren't very fine or well tuned, because after 1 million iterations, this bot is just somewhat adequate. A random bot beating it 700 times is not good. Interestingly though, then I took a fresh model again, MTQ table and policy, and I only ran 50,000. So it's quite a lot less, 20 times less training, but it was against the Minimax bot. Now the Minimax bot has strategy, so it's not just random. Remember, the early games of 2 untrained things will be completely random, and it's a bit more chaos than anything. And it ends up training where it might say, yes, this is positive, you won, but in the lead up to winning, if the other player had any form of strategy, there was a move for them to win. So it's actually a poor state we're rewarding positively. Whereas Minimax, immediately it's strong opponent, we're learning from a strong opponent, and after 50,000 games, he was unbeatable by the random bot. So that was interesting to note. So basically the highly trained bot, I've ended up taking this 50,000 as a base. Then I ran a few games. I say a few games, it's only about 50 games of human player against it, and then finally I ran another 1 million against that trained bot already, against itself, another 1 million, and that's where the highly trained policy comes from. And then just looking at the implementation details, if you wanted to see how I've done that, which is not related directly to Q learning in any way, it's just around how I've hosted it and implemented it. So on the web server, when I load the models, I've created a HTTP trigger function, and basically when you do a get on QLearn with a level, so that's either partial, solid, or community, we will then load from the server the policy and send it back down to you. And then for the community one, I've allowed a post to community where you upload your policy and we save it back on the server, which then just allows that every time you play against the community bot, it gets retrained. And then also then on the implementation side, I've let me just quickly go over here. I think it was in I've used session storage. So that's just a little optimization where you'll see when you load it the first time, if you go to your application tab and in session storage, you'll see the models over here. And the idea was that you can then, once you've loaded it once, it's actually on load that I just pull the stuff down, then everything happens on your browser. So the beauty of Blazor, once again, is that when I'm playing over here, for instance, against the Sum training bot, all of this is happening client side, and you won't see any network traffic. So it's completely on the browser. Oh, sheesh. First game I beat this guy, so not very good. Not a good start. Oh, and again. So this guy's not so solid. Let's see if he'll choose there. Okay. He has some form of strategy at least. So you'll see that there's no HTTP traffic. There's no calls to the server because we've loaded the models. They're actually in memory now. But if you were to, start a new game or go back, we'll load it from session storage and not have to pull those policies down again. And then that's it.